Welcome back, Raj. So we are starting our new chapter, which is actually about transformers. So I'm sure you guys must have seen these devices while you're like roaming around on roads, like or just like going to home, maybe at the end of the street or inside of your building power room. Okay, so these are basically the transformer pictures. Okay, different kind of the transformer. But this is a power transformer, power transformer. This is a measurement transformer, distribution transformer. Transformer, we briefly touch about this concept in the first chapter, is basically a device which is convert the mechanical energy to the electrical energy. Okay, that is actually the main purpose of the transformer. But besides that, we also use the transformer in the power distribution networks. Okay, like for the step up and step down voltages. So in this chapter, we are going to learn more about that what is the importance of the transformers in our life. What are the different types of the transformer with respect to construction and operation? What is an ideal transformer? Theory of the operation of the transformer, and then we will learn about a very important thing, equivalent circuit of a transformer, that how we can develop that, how we can analyze that, and what are the concepts about voltage regulation, efficiency, and finally we will touch the auto transformer. So transformer in brief definition is basically a device which converts the AC electrical energy from one voltage level to another level. Okay, for example, typically at the power generation, okay, like this is a plant of the power generation. So typically we generate the power at the 11 to 15 kilowatt level, very low level. Then we distribute, okay, these are the distribution line. Let's say this is the consumer. This is a very basic diagram. So then we distribute using a very high voltage lines. Okay, typically it ranges up to 700 kilowatt and typical range is like 110 to 220. So we make the distribution at high voltage levels. Why? We discussed this thing in last chapter also. So basically we want to minimize the line losses. Line losses is basically is equal to the I square R. So when we increase the voltage to very high, the current level decreases. And that actually minimizes the line losses. So that is the reason of the use like this is actually the beauty of the transformer, that we can step up the low voltage. So here we can step up to high voltage level, and then here we can step down, okay, at the consumer end. So this is the basic operation of the transformer. And if we look at the very basic internal structure of the transformer, so basically we have a ferromagnetic core, ferromagnetic material, and we have two ends of the core. So at the both ends we wrap the wires, okay, or like a coil of wire. So this is called actually the primary end of the transformer, primary side or primary end, and this is the secondary side of the transformer. Okay. So as you can see that these both coils don't have any direct connection. So basically what is happening when the current flows through this coil, so then the flux is actually induced inside the core. So that changing flux, okay, here this changing flux will induce the voltage in the secondary side, and due to that voltage eventually the current will start flowing at the secondary side. Okay, so basically the rate of change of flux is inducing the voltage at the secondary end, and the induced voltage, we learned Faraday's law, that this is basically equal to the rate of change of flux. And if we have n number of turns, for example primary side, so we'll have the n times of that. So n1 is the number of turns at the primary side and n2 are the number of turns at the secondary side. So typically the rate of change of flux is basically is equal to the ratio of the primary side voltage divided by the number of turns of primary side, or it is equal to the secondary side voltage divided by the number of turns of the secondary side. Okay, and the ratio of basically the number of turns of primary with the number of turns of secondary. This is called turn ratio of transformer, and usually we represent using N or A. Okay, this is also the ratio of the input voltage to the output voltage, or primary voltage to the secondary voltage. Okay, this is called turn ratio of transformer. And this is a very important thing, that why this is a very important parameter which actually defines that whether we are doing step up or step down operation of the transformer. So basically, usually the transformer change the AC signal to high voltage or the low voltage. Okay, step up or step down. So the question is, what will happen like if the input voltage is DC? Okay, what will happen in that case? Will transformer works or not? Okay, so think about this and we will discuss in live session. So why the transformers are important in modern life? Okay, so this is actually like why the transformers were actually developed, what are their applications, why we use them. Okay, so we will discuss these advantages in the live session. Okay, we will have this discussion in live session, that what are the basic importance of these transformers. So when you talk about the types, okay, so more common type of the transformer is basically the core type transformer. So okay, there are two types of the transformer. Basically, with respect to construction, we can divide them into two types: core type and the shell type. This is basically the distribution based on the geometry. So the core type look like this one. Basically, we have a core. This is primary winding and this is secondary winding. Okay, like this one. Okay, so this is a core. So these are the primary number of turns. These are the secondary number of turns, primary voltage and secondary voltage. This is an actual picture of a transformer. Okay, so this is core, and inside we have the insulation. This is the secondary winding, and here we have the this side we have the primary winding. Okay, so basically windings are wrapped around two sides of the core. Okay, these are the two sides of the core. So here we have the wrapping of the windings. The other is shell type. Shell type is basically this is a three-legged laminated core. Okay, with winding wrapped around the center leg. So basically there we have three legs, 1, 2 and 3. So here we have the winding rounding around the center leg. So like this is the primary winding and this is the secondary winding, and inside we have the laminated cores. Okay, like this one. So why we do the lamination? Because we want to minimize the eddy current losses. Okay, we want to minimize the path of the eddy currents. So this is just like the two types. Each type has some advantages. So basically, if we are doing the laminated core, it's become easy for us to insulate the high voltage windings from the core. Okay, and it will help us in less leakage of the flux. And then based on the operation of the transformer, we can classify them into different types. Okay, substation transformer, distribution, potential and current transformer. We will discuss them, okay, in the live session. So these are some kinds of the transformer, like three-phase substation transformers. So let's have a look at an ideal transformer. So as I said earlier, in ideal transformer we have a core, we have a primary winding, primary voltage, primary number of turns, secondary winding and secondary number of turns. We have primary current and we have a secondary current. So ideal, we are talking about a lossless device. Okay, so for example, the current is flowing, we are the flux is being generated, that flux is generating the inducing the voltage at the second end. Okay, there is no loss of flux. Okay, so and the ratio of the primary voltage over secondary voltage, or number of turns of primary or number of turns of secondary, this is called turn ratio of transformer. Okay, this is called turn ratio of transformer. So this is a typical symmetric diagram, and this is basically dot notation or circuit diagram. This is a dot notation diagram or circuit diagram, a basic circuit diagram of transformer. So we have same thing, primary voltage, secondary voltage. So here we represents the coil in terms of the coupling, that we have the number of turns of primary, number of turns of secondary. So these dots basically represents the direction of the current. Okay, so for example here if the primary current is flowing into the dot end of the primary, Okay, so here we can see that the primary current is flowing into the dot. Then the secondary current also flows from dot to the second end. Okay, this is just a dot notation, just tells us the flow of the current. So sometimes in circuit analysis we use this notation. So we are talking about the lossless transformer. So lossless transformer means the input power of the transformer will be equal to the output power of the transformer. Okay, so this is the basic assumption of a lossless transformer. So input power is equal to the output power. So input power is basically the multiplication of the primary voltage and the primary current, and the output is the secondary voltage into secondary current. Okay, and we know that ratio of the primary over secondary. Okay, this is basically the turn ratio of the transformer, right? So let's say this is our equation 1 and this is our equation 2, right? So what we can do here, like here if we take the ratio of primary over secondary, okay, so that will be equal to basically secondary over primary, right? And what is this ratio of primary over secondary? This is basically the turn ratio. So basically this is equal to turn ratio. So if we talk about the turn ratio in terms of the currents, so it will be the ratio of the secondary current divided by the primary current. This is the important thing. Okay, so turn ratio we can define in terms of the voltage ratio or current ratios. In terms of voltage, it will be the ratio of the primary voltage over secondary voltage. In terms of the current, it will be the ratio of the secondary voltage divided by the primary current, or number of turns of primary, number of turns of secondary. So there are three formulas for the calculation of the turn ratio of a transformer. So in the ideal transformer, because the input power will be equal to output power, so we can actually derive this relationship. Also, we can represent the transformer, okay, in phasor form. So in phasor form, we have know that we just like place the phasor notation on top. So this is a phasor voltage, primary side phasor voltage, secondary side phasor voltage. Okay, but we can write that secondary side phasor current or the primary side phasor current. So these are just the different notations which we can use for the analysis of the transformer. And if we talk about the power in an ideal transformer, so basically input power, like if we include the power factor also, so input power basically, as I said earlier, is the multiplication of the primary side voltage and the primary side current. So if we include the power factor also, it becomes cosine of theta p. So theta is basically the angle between voltage and current, and this is basically the power factor of a cosine theta t just represents the power factor. Similarly, at the secondary side voltage multiply with the secondary side current and the secondary side power factor. Okay, theta is basically the angle between Vs and Is. And in the ideal transformer, so basically because there is no loss, so the power factor at the primary side and the power factor at the secondary side will be same, or in other words, theta p and theta s will be same, or their difference will be 0. Okay, if we talk about an ideal transformer. Okay, so in the ideal transformer, whatever power factor we are getting at the primary end, it will be the same at the secondary end. Okay, so we can actually so basically if you remember, when we talk about complex power, so we have real power and the this is real power, this is our reactive power. Okay, so this become complex power, real power, and this is our reactive power. So this is basically our real power at primary and secondary end. Similarly, we could have the reactive power, and if you guys remember, so if you want to represent reactive power, it will be Vp Ip sine of theta p. Similarly, if you want to reactive power at the output, it will be Vs Is into sine of theta s. Okay, so reactive power we usually present using sine, real power using cosine, and sum of real and reactive is basically the total complex power of the transformer. So this is just the basic relationship. And when we talk about the ideal transformer, so basically the input complex power will be equal to the output complex power, okay, or like this one will be equal to the other one, okay. And if you are lossless transformer, so input complex power will be Ip into Ip, output complex power will be Vs into Is. So last thing is this lecture is, okay, the impedance transformation through a transformer, okay. So we will see this impedance transformation in the live session, and we will solve an example related to this in the live session. Thank you very much for your time.